In this video, we will apply Thevenin and Norton equivalents to the analysis of a circuit. For the left circuit, we have to calculate the voltage VCD, which is across the resistor RL for different values of RL equal to 10, 20, 30, 40, and 50 ohms. One way to solve this circuit is to analyze the circuit on the left repeatedly for 5 different values of RL, and it is possible to do so. However, we will show that it is much easier to calculate the Thevenin equivalent or the Norton equivalent of the circuit inside the dotted box and then solve the circuit for multiple values of RL. Since we have to solve the circuit for multiple values of RL, we will keep RL outside the dotted box and everything else inside, and we have two terminals C and D coming out of the dotted box. Note that we have to disconnect RL and calculate the Thevenin equivalent of everything inside the dotted box. Therefore, we remove RL and show the circuit on the right hand side, for which we have to calculate the Thevenin equivalent. Also recall that for the Thevenin equivalent, we have to calculate the open circuit voltage across the terminals C and D and the short circuit current flowing between the nodes C and D. We begin by calculating the open circuit voltage first. We will use nodal analysis to analyze the circuit on the right side. We begin by selecting node D as the reference node, and we have to calculate the nodal voltages VA, VB, and VC. Node A is connected to a grounded voltage source, and we can write that VA is equal to 72 volts. And we do not write a KCL at this node because we know the voltage. And also, it is not possible to write KCL in terms of the nodal voltages and other known elements at node A. Next, we write KCL at nodes B and C. KCL at B, we will assume all currents are leaving node B through the 3 resistors. And the first term will be VB minus VA, which we know is 72 volts, divided by 5, plus the current leaving through the 20 ohm resistor, VB by 20, plus the current leaving through the 8 ohm resistor, which will be VB minus VC by 8 is equal to 0 to satisfy KCL. Next, we will write KCL at node C, which will give us, assuming all currents are leaving node C, will be VC minus VA, which is 72 volts, divided by 12 ohms, plus VC minus VB by 8 ohms is equal to 0. This gives us two equations in two unknowns. The unknowns are VB and VC. We can solve them. The solution of these two equations will give us that VB is equal to 60 volts and VC is equal to 64.8 volts. Therefore, the open circuit voltage VCD is equal to 64.8 volts is also equal to the Thevenin voltage VT. We will calculate the short circuit current between the nodes C and D by putting a short circuit and calculate the current ISC as shown. Once again, we will use nodal analysis and choose node D as the reference node. Node A is connected to a grounded voltage source, so VA is equal to 72 volts again. Since node A is connected to a grounded voltage source, we do not write a KCL at this node. Nodes C and D are the same node because they are connected by a short circuit, which leaves only node B at which we will write a KCL. KCL at B will give us the current leaving through the 5 ohm resistor will be VB minus 72 divided by 5. Current leaving through the 20 ohm resistor will be VB over 20, and current leaving through the 8 ohm resistor will be VB divided by 8, which is equal to 0 to satisfy KCL. This is one equation in one unknown, and we can solve for VB is equal to 38.4 volts. Once we have solved for the nodal voltage VB, we will write a KCL at node C to be able to calculate ISC. KCL at C will give us current leaving through the 12 ohm resistor will be VC minus VA. VC is equal to 0. VA is 72 volts, so 0 minus 72 divided by 12 ohms. plus the current leaving through the 8 ohm resistor will be 0 minus VB, which is 38.4 volts divided by 8 ohms. And the current ISC is also leaving, so plus ISC is equal to 0 to satisfy KCL. We can solve this equation for ISC and it will be equal to 10.8 amperes. Recall that the open circuit voltage VT was equal to 64.8 volts. We have the short circuit current as 10.8 amperes and the Thevenin resistance RT, which is equal to VT over ISC, will be equal to 64.8 divided by 10.8 is equal to 6 ohms. We can now draw the Thevenin equivalent of the circuit between the nodes C and D. The Thevenin voltage is 64.8 volts. The Thevenin resistance is 6 ohms. And this is the Thevenin equivalent between the nodes C and D. Carefully note that the polarity of the Thevenin voltage source is the same as what the voltage will be across terminals C and D for the circuit for which this is an equivalent. And also, if we place a short circuit between node C and D, then the current will flow from node C to D. Once we have the Thevenin equivalent, we can reintroduce the resistor RL and connect it between nodes C and D, and recall that we have to calculate the voltage VCD for different values of RL. We recognize this circuit as a voltage divider such that VCD will be equal to RL over RL plus 6 ohms multiplied by the Thevenin voltage 64.8 volts. We will tabulate the results of VCD for different values of RL. And the results we will get are shown in this table. To summarize the circuit analysis that we have done, we were required to calculate the voltage across a resistor for different values of that resistor. We performed the analysis by first computing the Thevenin equivalent of the circuit without the resistor RL, and after computing the Thevenin equivalent, we reintroduced the resistor RL back into the circuit and compute the voltage across it for different values of that resistance. We can also calculate the Norton equivalent of the same circuit. Recall that the Norton equivalent will be the source transformation of the Thevenin equivalent. We will have a current source in parallel with the resistance. The resistance value will be the same as the Thevenin resistance, or 6 ohms. The value of the current source will be the voltage source value 64.8 divided by the resistance value 6, which will be equal to 10.8 amperes, and the direction will be pointed upwards to give us the same behavior between the two circuits.